Hi everyone, I am Sanya Kuller, and today I'll be talking to you guys about equal width binning, which is one of the ways that we can discretize continuous data. So go from continuous data all the way to categorical data. So put it into categories that we can count. So I'm putting numbers into bins, for instance. I'm going from categorical data, and how do we get that from all this continuous data? So equal width binning is one of the approaches that we can use. So just to kind of explain what are continuous and discrete values. So a continuous data value. A set of data is said to be continuous if the values belonging to the set can take on any value within a finite or infinite interval. So it's like something measured, right? It can be anything. You can go for pi, you can be like 3.14142. And I think at some point you can even find your birthday in pi, or your home number, or all sorts of things you can find when you look into the digits of pi. It's something really cool. So that's continuous because you can slice an interval, you can go down to the decimal place, and decimal places can go on for infinity, right? So if we're like thinking of a height or just something, that's continuous, right? So not exactly countable. So it's like any value. It's measured like 5.6, 2.489. Think of temperature, right? Things are like decimal places, and you can keep on going down to the nitty-gritties for the decimal places. So that's continuous. And discrete, I said, no, not that's not what discrete here is, but we're talking about discrete in terms of categories. A set of data is said to be discrete if the values belonging to the set are distinct and separate. So it's counted, it's countable. So you have specific values. You can count them. 1, 2, 3, 4, 5, 6. You can count, for instance, the number of cats. My older sister has a very cute cat called Bandit. And this is just it's so cute just to see this cat, hugging and cuddling, little teddy. It's just so adorable. It just makes my heart melt. So this is just absolutely adorable seeing, this cat. He's reaching out for his teddy, and it's just so adorable. I can't help it. Just so cute. So that's what discrete is. You can count it. And that's what continuous is. It's not exactly countable. You can go down to the decimal places, but for discrete, you can count it because you can have whole cats. You can count the number of cats. You can count the number of people. It's just like you can count something. So just to explain a little bit more, and this is Magic School Bus, one of the shows from my childhood, kind of dating myself. No pun intended, I guess. I love puns as well. But we have these types of quantitative variables, discrete again and continuous. So a discrete variable is characterized by gaps or interruptions in the values that it can assume. Like between one cat and two cats, it's one cat, two cats, three cats, four cats, right? It's like we don't have 1.15 cats or 1.156 or 1.3 cats or 1.4 or 2.4 or 2.9 cats. We only have 1, 2, 3, 4 in the number line. But so if I sketch this number line out here, what we do is we can see, okay, well, along this number line, we have this is 1, this is here is 2, this is 3. So discrete is going to be for instance, so this is a 3, but the sketches this is going to be yellow. Actually, let me show it this way. This is going to be yellow here. This is what discrete is. Discrete is this value here, and also this value here. And this value here. That's what discrete is. Discrete are these values here. That's what a discrete variable is here. So for when we look at discrete, this is what we mean. That's what a discrete variable is. Now for a continuous variable, so again for the discrete, it's going to be this value, or it's going to be this value here too, or it's going to be 1. It's not going to be anything along this interval. That's the difference. For continuous, it can assume any value within a specified relevant interval of values assumed by the variable. Like, so it's going to be able to, for instance, like, for the continuous one, like it could be any of these. It can be any of these values across 1 to 3, for instance. Any of those. That's what a continuous can be. So it can be height, weight, skull circumference. No matter how close together the observed heights of two people, we can find another person whose height falls somewhere in between. So it's almost like, like you could find somebody whose height goes down to the slightest, like, millimeter. That's what, like, on continuous, we can say we can go down to the nitty gritties. We can go down to the smallest, atoms. Like, that's what you can do with continuous variables. And when we're trying to discretize, when we're going essentially from here to here, from continuous all the way to discrete, this is called discretize. So we're going to have some data like gene expression data, for instance, and we're going to want to put it into bins, into numbers. Like we're going to want to have like, bin 1, bin 2, bin 3. This is discrete, bin 3, bin 2, bin 1. We're going to talk in our example about having 4 bins. And this, again, this is the process that I called, it's going to be discretization. That's what this process is. It's going all the way from a continuous value, it could be any value along here, all the way to these discrete, this is a value, this is another value here, this is another value, this is another value, this is another value right here. That is discretization. So we're going all the way here from all these continuous values here, any value here that's all continuous, all the way to these discrete values, where these discrete values are defined by, here and here, sorry, and here and here and here and here, here, here. Like all these values are discrete. That's the, this is the process that we're calling discretization. And there are 2 main methods that we're going to discuss, and I'm going to cover one in each video. So one is equal width binning. But for equal width binning, each of these bins has the same width, like it's 10 here, 10 here, 10 here, 10 here, 10, 10, 10. This is how like a histogram typically works, So this is 10, 10, 10. This width is the same. Like just almost like a histogram. But for equal depth binning, what you will observe here is that they may not have the same, and going across the y-axis is the number of items inside those bins. So again, this is also the number of items. So what you will observe is that for equal width binning, they may not always have the same number. So this 10, just to remind you, this 10 is basically the interval. That's 10. That's 10. That's the interval. For equal width binning, they all have 10 here for the intervals for this example. And, this is the number of items, the number of values here. That's what this height represents. But for equal depth binning, what we observe here is that all we really care about is having the same number of items inside each bin. It doesn't matter if this one is 22 long, or this one is like 9 long, or this one is 6, or this one is also 6, this one is 4, 7, 7, 8, 18. It doesn't matter. All that. So again, just to clarify, this is this is 22. Then this thing here is 9. Then this thing here is 6. Then this thing here is also 6. This thing here is 18. And this is 7. So it doesn't matter like what the width is here. What they care about in equal depth binning is each bin has the same number of elements. So the difference is each bin has same width. And here, each bin you should have like roughly the same width. So it really depends. If it's something odd or something, each bin has same number of items. That's what the thing is, that for equal depth binning, what we're concerned about is that each bin has the same number of items. We don't care about the width of the interval. It could be 22 or 9 or 6 or 6 or 7, for instance, or 18. It could be really long, really wide, really chunky, or it can be small. We just want the same number. We just want bins with the same number of items inside them. But like that's the same number. We're really caring about this height. This is what matters. So what we're caring about here is ultimately, what we're caring about is this. We're caring about, let me show this. We're caring about the height. We want the height to be the same. That's what we care about here. So they should all be the same height. That's what we care about. But for the equal width binning, what we care about is this. We care about the width being the same width. That's what we're caring about, this width. This width. That's the difference. So again, equal width binning cares that each bin has the same width. And again, if it's an odd issue, they should roughly be the same width. And equal depth binning cares that each bin has the same number of items inside it instead. So I'm going to kind of explain more about each of these. And another way to sort of compare equal frequency or equal density binning and equal width binning is the following. So like bucketing, the concept that we're talking about, and I have another video about equal density binning, it's just like a data pre-processing step. And you're basically discretizing data. So you're dividing the data into small intervals like bins. So it's continuous data that's going across like this. And you're basically dividing this data into these bins. You know, you're trying to divide them up into these bins. You're trying to discretize it. And then they are replaced by general value that's calculated for that bin, maybe a bin average, maybe a bin interval itself, maybe the bin number. This smooths the input data, may also prevent overfitting. You know, if you have continuous data, maybe put the data into groups, make it less specific, make it more generalizable. So equal frequency binning, which is also called equal density binning, that I have another video on. You know, bins have equal frequency, so equal number of items in each bin. And equal width binning, I think of it's like a ruler as well. You know, it's like placing these buckets out. You know, and rainwater could fall into these as well. You know, they're placing, you know, buckets of equal size. You know, they're not quite the same, but it's like placing them out and making sure that equal items fall inside it. That's what equal frequency is. Equal density, that's what it's called. So if we have the same list here, how would you divide it into 3 bins so that each bin has roughly the same number, 4 items in each bin here, equal number, that's equal frequency. Equal width is how do you sort of design the bins so that each bin, if you have 3 bins, that each bin has the same width and then the same number of items may or may not fall into it, but it has the same width. So maybe buckets of the same, you know, maybe this might have more than this, but if you look at them, that they typically have the same width. That's what we're focusing on here in this video, is equal width binning. Like here in this video, we'll be just focusing on equal width binning, uniform binning, and in the next video you may see my video on density binning, which is frequency width binning. So I'll just give you a little bit of a flavor for what is density binning as well. So I'm just going to talk about that very quickly here, but there's another video dedicated just to density binning. But our focus in this, again guys, is just on equal width binning. That's our focus. Geeks. So here I kind of want to talk about, feature engineering, deep dive into encoding and binning techniques. So basically, when we're using like machine learning models, for instance, we can do feature engineering, where we can do feature encoding, going from categorical to continuous encoding as well. Like one-hot encoding is very popular for neural networks as well. But pretty much in that kind of encoding, if you have multiple classes, like if you have, classes, like 3 classes, for instance, like in one-hot encoding, what you would do is if you have like classes C1, C2, and C3, then the way that you would encode having class 1 would be 1, 0, 0. For class 2, you would say it's 0, 1, 0. And then class 3 would be 0, 0, 1, for instance. So that would be one hot encoding. So there are multiple different encoding strategies that you can have. And here, what we're going to focus on is like going from continuous data all the way to categorical data to like this feature binning. And we're going to do like equal width binning and then frequency width binning. So equal width binning is also known as uniform binning, and density binning is also known as frequency width binning. So you're sort of, like binning so that you have the same number of objects in each bin. And equal width binning is your binning so that each bin is the same size. So what this is telling us is like, equal width binning again, and credit goes to Satyam Kumar as well for this slide here. And this algorithm for equal width binning is just dividing a continuous variable into several categories having bins or a range of the same width. So this is a way to discretize, to go from continuous data to categorical data. So you have your maximum value and you have your minimum value. And again, this is defined as our range. This part here is the range of the variable. This part here is the range. Min minus max. And x would be like the number of categories. So this x part here is the number of categories that we want here. That's what this x is. That's what this x is. And this little is sort of like kind of telling you how this equal width binning should be done so that you have roughly the same number of items in each. So you have roughly the same width in each bin. So equal width binning is making sure that each bin has the same width. So let's say that this whole thing here from this point to this point is like this whole interval is supposed to be like the min to the max. I want to like kind of divide it up into these chunks that are equal. So this is not exactly equal, but they should all be the same, roughly. But you want them to be equal chunks. So this means that it is inclusive, and so this is sort of like a formula, like min, max on the list, and that's how we do equal width binning. We just figure out, okay, well, roughly what would be the widths, and that's sort of how we define these categories. And I'm going to kind of explain it more. So yeah, this is just another example again about equal width binning when you're given this list of these values for x. Okay, and we want to put them into 4 bins. Okay, so we want to put this value into 4 bins. So we want to discretize these values here into like age bins, for instance. So these are the values sorted from least to greatest. And what we want to do is we want to find these bins. So what we do is we find the maximum value here. The maximum value is going to be, so the maximum value here is going to be at 55. So that's our max value, 55 is our max. And our min value is going to be 10. So if you take 55 minus 10, that's 45. 45 divided by 12, so 55 minus 10 divided by 4 is roughly 12. So that's sort of like the formula that's being used here to figure out the width of each bin. And what you want you to observe is that each bin, they have the same width of 12, roughly 12 units. But the number of items in each bin may not be the same. It really depends. So here there's 4 items in this highest bin, and then 2 in this third bin. Like 1 here in the second bin, and I think 1, 2, 3, 4, 5, 5 in this bin 1. So that's equal width binning, that each bin has the same width, but may not have the same number of items inside it. And one of the popular ones is actually histograms try to represent equal width binning. And then we can kind of compare them, like this is Python code kind of using this age. If you have that age variable, this sort of shows you how equal frequency binning works and how equal width binning works. So it's sort of the opposite idea that equal width binning, you may not always have the same density in each bin, but each bin is going to have the same width along. It's just like the same marks. You might not have the same, like it's the same way of binning information, like kind of putting continuous data into groups or categories, for work. So equal width, they just have the same width, but we may not have the same number of items inside each bin. But equal frequency, on the other hand, is saying that each bin has the same number of items. I mean, it's really trying to, if it can be divisible properly, it is supposed to typically have the same exact number of items inside it, but the widths of these intervals might not always be the same. As long as each one has, you just sequentially put each one in the bin, the next one in a bin, the next one in a bin, the next one in a bin, so that you have the same number of items. And this one is just like, okay, we have the bin max, we have the regions, we're just going to assign whatever comes in this region, like there, it just, everything has equal width. And it's just Python code as well. Like if you want to kind of look at the comparisons of, these are two of the main binning strategies we're going to talk about today. But instead, we could also just look, instead of the different stages, for instance, just pretend we're looking at different time points for 5 genes. So this is an example we're going to try to work through. Like how will we find the mutual information and calculate it between these genes? So we want to calculate the mutual information between all pairs of genes. And then, so here we're just going to pretend like we really don't know who's the transcription factor, and we're just like which ones aren't. So we're just going to calculate the mutual information between gene 1 and gene 2. Gene 1 and gene 3, gene 1 and gene 4, gene 1 and gene 5, for instance. Then we want to calculate that information between gene 2 and gene 3, because remember that we already have it between gene 1 and gene 2. Then gene 2 and gene 4, gene 2 and gene 5. And then we also need to calculate the mutual information between gene 3 and gene 4 and gene 3 and gene 5. And lastly, we need to calculate it between gene 4 and gene 5. So the way that we can do that is by sort of looking within this given gene, and we can sort of do some binning first and say, okay, well, let's look at the expression of these different genes. Let's see how they are in terms of their expression levels throughout, these time points from 0 to 150. We can look at time points maybe for the same individual at different time points. Maybe like this guy, we can focus on his Alzheimer's disease progression. And I know these timings do not make sense, but pretend we're looking at 5 genes. We're basically looking at all the genes, but we're just focusing on a small toy example here, where we typically, this data would actually look much inverted, where it would look like kind of like the opposite of how it looks. So I really hope that instead you can see that it would look just like this, like a rectangle with way more genes than samples or time points. But we're just trying to show here that we have these time points, and we're going to try to analyze based on these time points and the behavior, what is the information, like like maybe at a certain time point, as this guy's getting older, we would notice maybe that there is some neurodegeneration or some phenomenon is happening, as we're going down in terms of the time. So we're trying to basically figure out how can we group these genes, and that's how mutual information comes in. So we're going to figure out first within each gene, how can we bin it in terms of its expression levels, like in terms of the minimum or the maximum values. Like we should assign these values to given bins based on the distribution of each gene, because each gene has its own distribution, and we want to use that information when calculating the mutual information. So we're going to discuss the 2 different binning strategies that we could use. So in this example, you'll be hearing a lot about genes and gene expression, and sort of taking the expression of the genes and kind of putting them into bins. In this example, equal width bins. So what is that exactly? So a gene typically is a segment of the DNA that encodes for at least one polypeptide. And that polypeptide may itself be a protein, or it may form part of a protein. Here you can see like these are proteins, not just the proteins that you're encouraged to eat, right? So what are those exactly? So part of that is just a little quick review of the central dogma of molecular biology. So we have DNA here, It can be replicated when the cells are dividing, or it can be transcribed, and this is what happens, transcribed into messenger RNA here, the part of the DNA that encodes, genes. So that is transcribed into messenger RNA. So the DNA sits here in the nucleus, and we have like like a king and a queen on a throne, and we have these messengers, messenger RNA that comes. It's a copy basically of that part of the gene that's transcribed. And then there's some splicing that happens, alternative splicing, and then introns are moved, kicked out, exons spliced together, and then the difference in how they're spliced together can give us different forms of genes. So don't worry too much about it that we observe. But we have this mRNA here that's that leaves, then it leaves the nucleus, and then it makes its way across. So that's a process of transcription, copying a part of the DNA, transcribing it into messenger RNA. And the messenger RNA then leaves the nucleus as a little messenger, gets a little bit processed as well, goes into these little cute little factories, ribosomes, and then get manufactured into proteins. They don't get manufactured, but they provide the recipe, the code book for the ribosomes to then call these tRNAs, transfer RNAs, to help assemble, proteins. Or polypeptides by stringing together amino acids. So every 3 base pairs of the messenger RNA encodes 1 amino acid, and then as a ribosome comes and translates that messenger RNA, a growing polypeptide sequence is formed, and ultimately that could become the polypeptide chain could become a protein, or it could just be part of a protein. So usually all that we know is that messenger RNA is then translated into protein by the ribosome. It's like a decoder. So, we can modify DNA, a section of DNA containing information is a gene. Transcription, I often study like transcriptional regulation. And then, RNA, ribonucleic acid, coding RNA, non-coding, but pretty much this process, this messenger RNA is often it's going to be transcribed into polypeptide chain that may or may not be a protein, but it definitely forms part of a protein. Some proteins are made up of multiple polypeptide chains, and they have lots of different functions. So sometimes you can measure the amount of a protein or as well in the cell, and then figure out maybe the expression of a protein is too much, too little, not even expressed at all, like what's really going on. And that's measuring gene expression, and oftentimes it's done by measuring the amount of messenger RNA, because there are other ways that you can control this process of translating the messenger RNA into a polypeptide. But usually the more messenger RNAs there are for the gene, the more expression of that gene that there will be. So it can be translated by the ribosome into proteins, and proteins pretty much determine all the things like expression of other genes are often done by transcription factors, which are other types of proteins that are involved in this step here. Traits, phenotypes that we observe, cellular function, that's all kind of done by genes. So here we'll be just talking about gene expression. So I hope that this will help you kind of understand that we're just looking at the expression of different mRNA levels of different genes in the cells. And we could look at them in disease states and regular states, but that's the domain that this video will be dwelling on. So I hope that this helps you guys. And please let me know again in the questions and comments if you have any questions on this at all. I'll be posting more videos on this to help you guys. And for all of these 5 different genes, for these 16 different time points in this example, we can sort of see what the typical gene expression levels are. So this is frequency, but what this really are, the y-axis, this is just mainly measuring like the gene expression values and frequency. So these are histograms. So this is known as a histogram. Each of these is a histogram. So what these histograms do is they come up with their way of sort of binning these observations into different bins over here. Like so they're coming up with their own binning strategies based on their binning
And you know, we can see gene 1's expression values, gene 2's expression values are here, gene 3's expression values, gene 4's expression values, and gene 5's expression values. So right off the bat, what you can see is that these go up to like 1, 1, and 1. So these are like, so these three, I'll just have like a little, maybe I'll use this color. These three have pretty high expression values going up to 1, whereas gene 1 and gene 5, their expressions, like this one goes to 0.5 and this one is 0.25, so they like have relatively lower expression usually. So if we want to compare how gene 1's expression is changing, it's pretty low in general for gene 1 and for gene 3. So if we want to see how these expressions are changing during the 16 time points, it won't make sense to just compare, okay, well, gene 1 is this value and gene 3, gene 4. It doesn't make sense, right? Like if you have somebody that you know who's really skilled, like let's say your parents or guardians are really good cooks, right? And you may or may not be, you know, please don't take offense, but like let's say that somebody who's been cooking a lot longer, right? For instance, is really good at cooking. So if that person is learning a new recipe versus you, that person is going to probably make it like a lot better than you could, because they're already going to be super skilled at it. Like one of the things I love doing is I love to knit actually. So this is my yarn here. So I'm trying to make something as well. But if somebody who doesn't know like as much like knitting, or who doesn't know as much of you know, like let's say you don't know enough cooking or somebody else knows it, the idea is that they're going to pick up like a lot faster than you in the same amount of time. The person who's skilled is going to pick up a lot faster than the person who's not skilled. So somebody who's learning how to cook a new recipe versus somebody who's skilled at cooking, learning a new recipe, the person who's skilled is going to learn it faster, right? So it doesn't sometimes make sense to compare these values of gene expression, especially when they're on different scales, right? Like if we had to say, oh man, like how come you didn't learn this recipe and this other person who's super skilled learned it better than you, or they made the dish way better? No, it doesn't make sense that way. It makes sense to say, okay, where did you come from? You're not as skilled at cooking. Sorry, again, please don't take offense. This is just an example. You're not as skilled at it, right? Or like for me, for knitting, this is my grandma. She is super, my paternal grandma, she is super skilled at knitting, and she can knit something that would take me like weeks and weeks. She can probably knit it in a couple of days because she's super, super fast, you know, at knitting. In general, she makes very beautiful sweaters as well. Like she's super skilled. And pretty much the idea is that something that would take her a much shorter amount of time would take me a longer amount of time. So everything is all relative. So the key idea is that we want to make sure we're looking at like on a typical level. You know, like if this amount of time takes me this much time to make the same material when I'm knitting, or if I'm cooking, or if I'm doing something, it might take somebody who's more skilled less time to cook, or it might take them, like my grandma, less time to do the knitting. So we shouldn't be comparing the quantities per se or the quality per se, but we should be looking at like the changes in general. Like, are we noticing that like I'm doing better? So my idea is that we're not looking at the absolute quantities for these. We're trying to find ways to bin these values and then compare them, because gene 1's expression is never going to be higher than gene 3 is not, I mean, never going to reach gene 3's level of 1. It's never going to reach gene 4's level of 1 either, or gene 2's expression of 1, for instance, or even gene 5's expression of 0.5 here. That's just not like how its value varies. But we should see over time, are we observing the same trends over these 16 time points? That means like when gene 1's values is going up relative to its other values, are we noticing the same behavior for gene 3 or gene 4 or gene 5 or gene 2, such that knowing something about gene 1's expression can tell us something about the expression of the other genes. That's what mutual information is telling us. Like in sequence logos, does knowing something about like a position along the motif, do we know more that that base is likely to be a given base or not? Like basically, how much information do we have? And if we know that gene 1 and gene 3 tend to move in similar directions, right? Maybe at a certain time point they really spike and then they go down. Maybe the cyclical behavior where they shoot up and then go down, shoot up and then go, shoot up and then go down, shoot up and then go down. Maybe it's cyclical, or maybe it's just increasing together. Maybe it's all decreasing. So it's like we want to compare how it's moving relative, right? So I can't compare myself with the experts in the world who are great at knitting or who are great at cooking, great at video games or great at sketching. Like if I made a star that looks just like this, I should be happy. Somebody else could draw a very beautiful star, right? But I'm getting better, which is nice, right? So the key idea is we want to bin these things into bins, like maybe using equal width, equal density, and we're binning it based on each gene's own values. And we're binning it based on its own values and based on its own values and based on its own values, respective values and its own values. And we're seeing how does its behavior across the 16 time points, how does that behavior change? And are there similarities in the changes between these genes and these genes and these genes and these genes? So we're basically taking all pairwise and then these genes and then these genes and then these genes and then like this and this and this and this and this. Like hopefully try to capture as many pairwise as possible, but we'll be basically looking at 1, 2 comparison of those genes. Then we'll be comparing 1, 3, then 1, 4, like those genes, and then 1, 5, and 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, and last but not least 4, 5. And what this is this is basically like this is a gene I. I can just write maybe gene A and then gene B. And we're just looking at all these combinations and we're just trying to figure out that's what we're trying to do. And again, these are like the expression values and our goal is to bin them. You want to put these into proper bins so that we can try to see how are they changing together based on their relative values. We want to bin them based on their relative values using either equal width or equal density binning. Those are two main strategies to bin them based on their relative expressions. Put them into bins. That's our goal.
So basically, now we have two different strategies that we can use to bin the values for each gene. So we're going to focus on each gene. For instance, like we have these 5 genes and we're going to look at gene 1 in this example. And then we're going to look at gene 2, 3, and 4, and 5. And for each of these genes, we're going to look at all of its values for whatever it is. It could be a set of individuals in different stages of Alzheimer's, for instance, or a bunch of different time points, or anything. It's just all that matters is that this thing is just either it's like different people, and we just want to find that the changes in these expressions along for these should be the same. They should follow the same patterns in general, because maybe this gene has a high expression level than this gene, for instance. So it just makes sense to say that relative to this expression, how is it changing in terms of its binning as we go throughout the time points? That's what we're interested in seeing. How does this change in its overall expression, looking at its minimum to its maximum? And like we're putting it in bins, how does this behavior change during time or during, as we are progressing from patients who have, no Alzheimer's to those who have Alzheimer's that's very severe. So like these conditions, as we're going down, these represent the similar conditions for these people. For these time points, and for these different genes, and we're trying to see if the behavior changes are the same, and then there could be some mechanism of transcription that could be taking place. But basically we're trying to calculate the mutual information, because if their behavior is going in a similar direction, where maybe these maximum, this is like maybe this is the maximum values are here, but it doesn't seem like here, it seems like this maximum value and this maximum, these are higher values, they're not quite moving in the same direction, for instance, there. So we would be saying, okay, like, so the one way to say is that, okay, this way we could look at it is we could look at the minimum values or the maximum values, and we could say, okay, well, it seems like 0.24, like these values seem like they're the higher ones. For instance, like these seem like the higher ones for this gene. And then for the other gene, maybe like what we see is like 0.92 is really high. It's got really high values. Is there any like kind of connection between these? You know, is there any kind of connection? Maybe I'll also just, for similarity, I'll also just, you know, highlight like 0.83, you know, even though it's a little bit off. There's a little bit more of a greater difference. So we can look at gene 2 and see, well, these maximums don't quite be, you know, tend to move in the same direction, right? So like the expression levels are on very different altogether at different levels. Maybe it's just the way that that gene is. So we want a fairer metric of comparison to say that, okay, out of all these expression levels for this gene, how is its behavior changing? Then for all of the expressions for this gene, how is its behavior changing during these time points? And then for this gene, how is its behavior changing, you know, like the maximums and all of that, like how is it changing? And do they tend to change in similar ways? So that's what binning is going to tell us. For each column, we're going to put these maybe into like we're going to put these in probably like a maximum bin. For instance, like a maximum bin could put these in one bin together. And then it could put other values like the second tier in another set of bins, and then the third tier, and then we'll have one for the smallest one. That's what we're doing here. We're binning along each column. And there are two different ways for us to do this binning. One is equal width binning, where the bins will have the same width along, you know, like maybe we want, like, you know, we look here and we divide it into equal set of bins, you know, with the width are the same. Maybe we take the min minus the maximum, and then we find the number of bins we want, and each bin will have the same width. And that could be a strategy that we just focus on, like, you know, they have the same width, and, you know, this is another bin with the same exact width, for instance. Actually, it don't quite look good, but the general idea is we could look at equal width binning or equal density binning. Equal density is saying that each bin should have the same number of genes in it. Like maybe we'll have the top 4, the next top 4, then the next top 4, then the smallest top 4, for instance. Oh, sorry, it would be like the top 4, then the second 4, then the third 4, for instance, and then maybe the bottom 4, like the minimum 4, for instance, like the lowest. There could be multiple ways to bin this data for each gene. It just matters that we do it in a consistent way. So we can either use equal width binning or equal density binning. And the important thing is that we figure out what is the optimal number of bins that we want to use, and what strategy do we want to try out.
So in equal width binning, what's really important is here we're not starting all at 0 like here. So it's a tweak. We're tweaking what this histogram looks like. So first things first, we're going to find what is our minimum value. You know, our minimum value of 0.04. So we're looking here for our minimum value at 0.04, and that's what we find here. We basically go on and we scan for the minimum value here. And then we also look for our maximum value, which we have is this value here, 0.24. This is our maximum value, so we just scan through what this whole thing is. We scan through it, we find a minimum maximum value. Other ways we can just like kind of, you know, sort through this from minimum to maximum. So this is min, and then all the way down we're going towards our max. And our maximum value is this value here. That's, right at the bottom. So then what we find is we take our maximum value here, then we subtract our minimum value, and when we take the difference between these points as we go down, that gives us our range, which will be, equal to 0.2051. That's what this range value will be. And then the width of each bin is just the range over the number of bins that we want. So in this case, they give us 5, but again, it's just like it's not starting at 0, but our minimum value will start here, and then we're going to go in the width of each bin. So we're starting it here, and then this is how we find the width of each bin. We're basically going to a maximum, and we're dividing this region, this whole range here, which is 0.20521. That's what this difference is from here to here that we're traversing. We're going to divide that into a set number of bins. So the way to do it is to take this overall difference we want to achieve, which is the range, and then divide it by the number of bins. That's how we'll do it. We'll take this value here, and that's how we're going to do it. So here for this equal width binning, so we're wanting to have these 4 bins. So again, what we do is we can sort these values here. So right now they're sorted by time from 0 all the way to 150. So we can sort them by value from minimum to maximum value here. So we can sort them from minimum to maximum. So we get the minimum, which is 0.044616 for gene 1. And the maximum for gene 1, which is 0.249826, and we have our range, and this is a number of bins. So since we want 4 bins, we're going to just divide by 4, and we're going to have the width of each bin being 0.051302. So that is the width of each bin.
So what we can also see is that for the minimum value and the maximum values of like 0.044616 and the maximum of 0.249826, when we found these widths, those correspond for equal width binning with 4 bins for gene 1 to having this bin having this interval from here to here. And then these are the intervals from for bin 2, and the intervals for bin 3, and those for bin 4. And you can see that they all have the same width of 0.051302. So they have the same width. So it's equal width binning. So based on this minimum and this maximum value, we found out how to reconstruct these bins here for for equal width. And this is for gene 1, so we'll get like different values for different number, like gene number, like gene 2, gene 3, gene 4, gene 5.
So for equal width binning, you can kind of think of it as this idea for this gene 1. So like you can pretend that it's raining, and we have these 4 buckets, these 4 bins that have equal width, and here the equal width for gene 1. So for these 4 bins, we found that the equal width would mean that each bin has a width of 0.051302. This would be the equal width. So that's what's shown by the ruler over here. And so we just line up these 4 bins, and this is like Oscar the Grouch. You can pretend it's a Sesame Street analogy in a way. I grew up, I love Sesame Street, so I'm really a huge fan. I'm gonna be a new aunt too, so that's exciting because I'm a first-time aunt, and I'm gonna have a little one on the way. So we're gonna enjoy watching one of these shows together. So that's so exciting. But in any case, imagine that it's it's raining outside, and these water droplets that are falling, and each of these bins is the same width. So maybe you can tell that this one's gonna probably get 2, and this one might have 1, and this one just really seems like it's just gonna have 1 droplet falling in, whereas this one could have 2 potentially. These could have 2. So it really depends where it's placed. So they have the equal width, and they could have, like, maybe one bucket can have more rainwater falling than others. It's just the luck of the draw. So that's what happens with equal width binning. You know, you have these buckets at the same width, and it's just you place them out, and some buckets may end up with more water than others because maybe it's more concentration of rains falling there, the wind and all that stuff is also impacting things. So similarly, the expression might be that maybe based on the distribution of values, some buckets will have more values than others, for instance, and we can get some of that intuition by looking at the histogram for each of these genes. So for instance, what you might realize is that it seems that for the beginning width, you know, like this is equal width, but they start at 0, which we're starting at the minimum value here instead. But what you can sort of tell is that a lot more values are concentrated in the later on values. So that's how this distribution looks. So this thing would be called a left skewed distribution. So an analogy one of my first stat professors had taught me is the idea of skewed left. Means that if you were skiing, if you're a little dude skiing, you would ski, yeah, that you just ski to the left. So that's like, it's more like a left tail distribution. So that's a little smiley like skiing down. So it's a skewed left distribution because like it's more spread out here. There's like less density towards the left side, and it's more concentrated towards the right. So it's like a slope going down. So you'll be skiing in the left direction. So here you would expect in these values, so typically as we're going across from here to here, what we would expect is that the values, the gene expression value is increasing. So gene expression is increasing. Increases. So let's actually see what happens when we are doing this binning. So it's an increase in gene expression value as we're going from left to right. You know, if we're going from here to here, there's an increase from left to right here. So let me tell you what these bin sizes exactly are.
So here for equal width binning, we're trying to create 4 bins for gene 1's expression. So here this ruler is measuring that, you know, the equal width binning, and these are what these intervals correspond to, as we talked about before. So this is the bin for bin 1. It's the first bin. This is the interval for the second bin. And this is the interval for the third bin over here, and this is the one for the fourth bin. So for instance, the first bin is 0.04461, 6311, all the way to 0.0959188. And each bin has a width that's equal, that's 0.0513024889. And that's how we got it. This is Oscar the Grouch, you know, it's an allusion to Sesame Street. So the idea is just like, you know, rain falling. And we don't really know like which bin it's going to fall into. There's wind, there's all these things that are happening. And we just want to see that they have the same, we're just having these buckets next to each other, and it's raining outside. You know, these rain droplets are falling, and we don't know, you know, this one over here is going to like fall here, or like, you know, go here, or like go here, or no, we don't know. It's like just a rainstorm in a way, and we're just lining these buckets out. They have the same width. Don't know how much water we'll get in the end. That's kind of the idea of equal width binning. So for instance, now let's look at the first time point, time 0 for gene 1. So it's 0.176955. So time 0, we have this raindrop here. This is its value. Which bin will this gene expression value at time 0 fall into? Will it fall in bin 1? Will it fall in bin 2, bin 3, or bin 4? Which one? This is its value over here. So what we're going to do is we're going to try out each of these, and ultimately we found, bingo, we found that it's going to fall in bin 3 because 0.01769548813 falls in the interval from 0.147222129 all the way to 0.1985237. So it falls right in this interval. So this raindrop is going to land in bin 3. So that is the value that we're going to assign at time 0. So here. So this gene expression value at time 0 would fall into bin 3. So that's what over here we've assigned it to bin 3 for this time point. And now we have the other time points to try out, and we just have to see which of the values, which of these intervals they respectively fall in. That's the goal of equal width binning. So here we're going to also do equal width binning for the next one, which is time 10. So that's this value 0.08509. So we're going to see, okay, well, which bucket does it fall into at time 10? So which value is 0.085009 in between? I think it's going to be this one, bin 1. And indeed, it is bin 1 because this value is in between this interval, middle and high interval. So that's why this gets assigned to bin 1. So indeed, we put bin 1. So it's this value at this gene 1's expression at time 10, which is this value, is assigned into bin 1. So it's one of the lower expression values for this gene 1 in terms of all of its other expressions. So all these, remember, all these bins are how we're going to bin it based relative to its own distribution. So this is equal width binning. And again, this is like the equal width. This is the width of each of these bins here. Then again, we're going to look here at time 20. We're going to see, okay, well, where does this value fall into here? And we're going to see, okay, well, I think maybe it's probably going to be bin 2 because it's in between this, this value is in between these two values. So indeed, it's bin 2. So we're going to assign it to bin 2. So that raindrop falls in bucket 2. And that's why we assign it to bin 2. And similarly, we just go through each of these values here and we just find out, okay, well, which of these bins is it likely to fall into? Or will it fall into based on these intervals? These are these interval values. Like for instance, this 0.185204 is going to fall in bin 3 because 0.18 is in between 0.147 and 0.19. So that's how we can finish doing all of the binning for gene 1 in terms of its expression values here. And these width binnings and these intervals, like minimum and maximum, are going to depend. So this minimum and this minimum value, this maximum value, it's going to really depend gene to gene. So again, you can sort of see that, based on that, we have 4 that fall in bin 1, 2 time points that fall in bin 2. We have 4 that fall in bin 3. We have 6, a lot of them that fall into bin 4 based on the width. So this is different from equal density binning where each of them would have had 4, 4, 4. That's sort of different. And now we can also focus on doing the same thing for gene 2 in terms of its equal width binning. So we're going to focus on this part here, equal width binning here, this part for gene 2. And now, as I mentioned, we're going to do each column, each gene separately. Its binning will be done separately. So again, we take the minimum value here for gene 2. We find the maximum value for gene 2. So we find the range is a difference between the maximum value and the minimum value. So this is the minimum value here. This is minimum value here. Maximum value here, all maximum and maximum. So this is the range. This range covered by the min to the max is going to be 0.809705. And what we do is we just divide it by 4 and we get the width of each bin. So here it's like sort of sorted by the time. Not by the time, but the gene expression values, and that sort of tells us how wide will gene 2's bins be, and you're going to see it's going to be different from what gene 1's width was. So here, based on this width and we just can derive what these bins will look like. So based on the width of 0.0202426, this will be the interval for bin 1, interval for bin 2, interval for bin 3, interval for bin 4. And I know like when it's equal to that value, those will be like boundary cases, and then it really depends on your implementation for how you want to incorporate them into the binning strategies. If it's equal to this value, do you want to have this, being greater, less than or equal to, or just a strict less than? How do you want to do that? That sort of depends on your implementation for it. But that's kind of how we do this equal width binning here, and that's how we derive the intervals. So that means the last one is going to go from 0.73659 all the way up to 0.939016. And again, we can do the same thing for gene, this gene 2. We have a updated width here, we have our updated intervals here, and we have these updated list of genes. And we're just saying, for instance, that for this value over here, 0.393809, it falls in bin 2 because it's going from 0.33 to 0.53, and this value falls in bin 2. Similarly, these maximum values will definitely fall in bin 4. The minimum value should definitely fall in bin 1. And then, for instance, like let's see here that 0.608, it falls here in this interval from 0.53 to 0.736, so it's going to be in bin 3. So that can kind of make sense here. Then we can just sort again to just to see how many values we get. So we have like 3 values for bin 1. We have 3 values also for bin 2. We've got like 5 values for bin 3 and 5 values for bin 4. So it seems like we have a lot of values, like using this binning strategy. Seems like we have like a lot more strategy, like this and this, and then like we have like higher for the other two bins, for instance. So it seems like it could be like skewed to the left, the guy skiing to the left in a way. That's what this will tell us for this gene 2. And now we can focus on gene 3 for equal width binning as well. So we're also not just doing it for gene 3, and then we'll do gene 4 and then gene 5, and then we'll have all the respective bins for each of the genes. So again, for gene 3, so here is sorted by the time, but here you can see that I'm sort of sorted the minimum and the maximum values. And then, minimum value of 0.030872, maximum value of, this 0.908 value here, the same thing here. We can find our range will be, going from the min to the max. This is covering 0.905 divided by the 4 bins that we want, and this is the width of each bin. We do the same thing where we start with a minimum and then end with a maximum, and then we use that width of each bin to derive like each bin's threshold. So typically something falls in bin 1, it's going to then be between this interval, it's going to be between like 0.003087. It really depends on your implementation, and this is value for the gene expression, and it really depends on what you want. So this could be like 0.22946. This is what bin 1 would be. Like that would be the interval, and if it's up to you if you want to be less than, or this is a point, or if you want this to be less than or not, or just strict. It's really up to you how you want to handle that situation here. But that's sort of like how bin 1 would work for gene 3. And the same thing, you can see that the width is changing. And we update the width here of like 0.226372232. And again, we're just binning, like these are all updated using the previous slide. Like remember, these are the intervals for bin 1. And the minimum as we expect is in bin 1, and the maximum is in bin 4. And for instance, this is in bin 4, this 0.8211, because it falls within this interval of 0.68 all the way to 0.908. That's why 0.82 falls in that, so that's why it's assigned to bin 4. So we're just going through, we're just assigning each value, based on, does it fall, within these bounds? Does it fall within these bounds? Like the raindrop, wherever it's placed, geospatially, does it which bin it's going to fall into, and we sort it again, like, just we're sorting it by the bins, and we can see that it really, like this guy here is really happy because he gets a lot of values in bin 4. It gets like 6 values, gets a lot of values. This guy got 5, he's kind of happy as well, and she's like kind of like 2, okay, and it's like, I only got 3 raindrops, Raindrops keep falling on my head. It's just like that same song that's in my head too. But that's sort of how you do binning for gene 3. We also do it for gene 4 as well, the same exact idea, where we look here and you can see here I kind of put the result here, but because it's the same idea, like we just look for the minimum value, we look for the maximum value, and then min and then max. We find our range, we find our width of each bin, and this is like the same idea for gene 4, like we find the width and the minimum and maximum values and the width of each interval. So we can kind of just like, take this value plus this width equals this maximum value. These two are the same. Again, so I'm just going to explain again how we get this. So we know that we have a minimum value here. We have our width of each interval. So that's how we take both of these values to then find what the maximum value is. Then we also know that this value would carry over here, and again, it really depends on you if you want to have this value like, like be included in this interval or not.
but like then this value carries over here. You use these two parts, 0.27997 plus this 0.224408 to give you this value. And then these two values are the same, here, and then this plus the width gives you this value, and then these two are the same, this plus this width. So the difference again between these parts here is going to be the width. So this difference here is going to be, distance from here to here is going to be your 0.22448. That's what it's going to be. Between this interval, this is the minimum value and maximum value for each of the bin intervals. Bin 1, 2, 3, and 4. And that's how we get it, like the minimum value plus this width of each, which should be exactly the same for each of the bins, will give you the interval for each bin. So the same idea, we adjusted our equal width, and we put those values into our respective bins here. And you can see again, like, as just to, sanity check, that this 1 corresponds to the minimum value here, and this maximum value here is corresponding to bin 4. And for instance, this 0.513 goes into bin 3 because it's 0.51 falls between 0.50 and 0.72. So that's why it goes into bin 3. This value over here goes into bin 3. So this kind of shows you again. So please let me know, guys, if you have any questions on how this works. Again, like 0.31096 is between 0.31. It comes between 0.27 and 0.504. So that's why this value gets assigned to bin 2. This 0.31096 gets assigned to bin 2. And you can see again here that, we have a lot of values in bin 4. We have these 7 values get assigned here. So here I'm just sort of wanting you to just see how it works, and that for equal width binning, you may not get the same number of items inside each bin. It really sort of depends, where the water falls, where the raindrops fall, where it all lands up, based on the distribution. All you're doing is just making sure that they all have the same width, same exact buckets. It just depends on where you place them. I really hope you guys like my analogies. I know they can be like hit or miss sometimes, but hopefully, I love telling like analogies and stories as well. And lastly, this is gene 5. So we're doing equal width binning, and we're focusing on its minimum and maximum values and then finding that range. As usual here, we can find this minimum value here. That's what this part is. This minimum value here is going to be this min here. And that's also the same minimum here. The maximum value here is going to be this value here is going to be the max. And the range is going to be this nice value here of 0.4341. That's what this that's what this value is going to be here. That's this range. We plug this range in over here, and we get the width of each interval in each of our bins, 0.1085 here. And that's what we use here, 0.1085. That's going to be the width that we're going to find. And these are the intervals for each of our bins for gene 5. So again, sort of just reiterating, you take your minimum value, you have your width, and that gives you this maximum value. That's sort of just reiterating, you have your minimum value here. That's what this part here is representing. Oh, sorry, this part here represents a minimum value. Then we have our width, which is what this column is representing, the width. And that gives you the maximum value, which will be here. So that's how we get it for each of these bins. And again, we updated our equal width binning. This is the length, the width of each bin. And this is sort of showing how our binning works out for gene 5. These intervals have been updated as well. And again, you'll see that the minimum falls in bin 1, maximum falls in bin 4. This seems like this is the only value that falls in bin 3 is at time 0.90 plus 0.273. It's pretty lonely, right? It's, So again, this value for this, this time 0.90, it's the only one that falls in bin 3 because 0.273 falls between 0.219 and 0.327. So that's why it falls in bin 3. It's the only one value. And same with actually bin 2. It only has one value here. Seems like a lot in bin 1. Don't know why this bin 1 is still unhappy. And then, a little bit fewer, but, still quite a bit in bin 4. So, when you combine them all for equal width binning, we can sort of see again, similarly, the behavior of the binning, based on these gene expression values and the equal width binnings. And they're all relative to the expression for each of these genes. So we think of it like sort of like how a histogram works. Only your min and is not like really at 0. They sort of like defined based on the minimum value here, but you can also probably tweak the histogram as well. But it's a similar idea of how a histogram works. And you can see how these behaviors are changing. Whereas, for instance, here, if we look at time point 10 for gene 1 and 2, and also 5, it's actually like the lowest value for gene 1, 5, and 2. It's, for gene 2, it's 1. Gene 1 is also 1. For gene 5 is also 1, but for genes 3 and 4, it's actually like in 4. So it's the highest value for genes 3 and 4. It's actually like one of the lower values for genes 1, 2, and 5. And hopefully over here, what you can sort of see is that we, just sort of, I was just mapping them between the two so you can have a better idea for how this looks, the comparison of gene expression values for all 5 of these genes here, how equal width binning makes them look here. And again, we were observing some interesting behavior, I would say, when it comes to like this gene here. These tend to be like a lower value for the time point 0. So this is just an example, like when you're given this data, like how would you tend to interpret, what's going on over here, so that's what we're going to try to do, is see relative to their expressions. These are their binnings relative to their own expressions. For these equal width binnings, we found their minimum value for each gene. Their maximum value is maximum value. Then like the number of bins, which we held constant for all of these as 4. So all of these bin values have to be between 1 and 4, 1, 2, 3, or 4, and these are all discrete numbers. So this is an example of us going from continuous data all the way to discrete. Is discretizing it based on the number of bins. And sometimes, like, in some programs you can write it where, you can slide the bins and you'll see how the histogram changes in its shape as well. So this shows how you're discretizing, so making it discrete, something countable, going from these numbers with these decimal places, like, on pi, you could go like 3.1412, like forever and ever. You're putting them into these discrete bins here, and so this is called discretization again, from continuous to categorical. But we're looking within each gene to get its binning. So the binnings are not like universal, like the widths were not universal. It was each gene, each gene's minimum value, each gene's maximum value, then defining that interval and then binning it there. For gene 2, the same thing, it's min and max, defining the width of each bin, and then kind of sorting them. So we did it for each of these, and we're going to then compare their behaviors relative to the other values. And that's what this is telling us, that these 4 are telling us that here for this gene 1, this is like one of the higher values it typically is. One is saying it's one of its lowest values. And that's what we're seeing here. We're trying to understand, like, is there similar behavior between, the highs and the lows, or anything that knowing information about one gene can tell us information about the other.
Yay, and yay, we have finished equal width binning. So think of it like a ruler, so each bin has the same width, basically. May or may not have the same number of items in each of the bins, but they have the same width. Whichever items come in, like rain buckets, rain falling, you just place out all the buckets of the same, same size, like circumference, radius. It's the same identical bucket, just place them around. And you may or may not get the same, if you have things in water falling, or the same amount of water may not always fall into each bucket. It really depends on the wind and other things. But that's the same idea, that you have buckets, you have bins of the same width, and however many items in each bin, that's what we stick with. So yeah, equal width binning. So thank you guys for powering through this with me. I really appreciate it. And I hope that this helped you guys.
Thank you so much for watching my video. If you like it, please subscribe to my channel, and be sure to like it if you really thought this was useful. So just signing off with my favorite logo, the smiley. So yeah, just thank you guys for watching. And again, I'm Sanya Kutter, and I'm really happy to help teaching and explaining certain concepts. So please reach out to me if you have any questions at all, and I'll be happy to help. So thank you for learning about binning and discretization with me today. Thank you, guys.